G'day there, Level 3 Physics. Time to roll on with a few more of these rotational quantities. This time, angular momentum. That's kind of really similar idea to linear momentum, the oomph of an object. How much rotational oomph has it got? How much tendency does it have to keep on rotating? And that's going to depend both with linear momentum, it depends on the mass and the velocity of a body. The more mass or the more velocity a body's got, the more oomph it's got, the more momentum. With a rotational body that's rotating, the inertia and the angular velocity both contribute to that. And so we chose a letter for angular momentum, the next free letter in the alphabet, which turned out to be L. And it's good because look, there's an L in angular momentum, so it makes sense. So L equals I omega. Unit for omega is per second. Unit for I, kilogram meters squared. Can you work out what that unit is for angular momentum? Because you're going to have to when it comes time. Kilogram meters squared per second. Is that what you got? Now the weird thing about angular momentum, similar to normal momentum, angular momentum is always conserved so long as no external torque acts on the body. Nothing speeding it up, nothing slowing it down. That means that angular momentum must be conserved. Weirdly, with a linear body, we can't just tweak mass. But with a rotating body, we can just tweak inertia, because we can change the spread of the mass in a rotating body while it's rotating. There's nothing to stop us making adjustments of where the mass is located while something is rotating. And so the trick with angular momentum is you can't always assume that that inertia stays constant. That inertia of one rotating body might change, even though the mass of that rotating body might change. Keep your eyes out for that. You might spot on your formula sheet that there is one other ridiculous equation for angular momentum which is very rarely used, but it does allow us in the occasional situation where you might have to link linear momentum to angular momentum. It allows you to do that. So on your formula sheet, it says L equals mvr, mass of the body, times by the speed it's going, times by the radius it is from the point of rotation if it's to start rotating. So this is kind of like a car driving onto a turntable, then putting on the brakes, and the turntable starts to rotate as a result. That's linear momentum being transferred into angular momentum. So keep your eyes peeled for that, but it's a pretty rare situation. I think it's useful to notice that mv is momentum, and so that L equals mvr is just the same as writing L equals p r, remembering that p is the unit for linear momentum. Now one last thing to add is the direction of angular momentum. In fact, it's the same rule we're going to use to find the direction of any rotating body, and that's the right hand grip rule. So get your right hand and grip those fingers, leaving your thumb poking out, and that thumb shows you the direction of the angular momentum vector, which is in fact along the line of the axis of rotation at right angles to the rotating body. And so any change in momentum or addition of momentum with angular momentum is complicated because the vector is in that direction at right angles to the rotating body. Don't expect to have to do those calculations this year. Let's do an example. Alright, here we go with our example then. Here's a physicist on the top of the high dive board, not worried about the small drop down to the water below. And they're rotating as they launch off. They're going to rotate with an initial angular velocity of 2 per second, and then realizing that they're not getting around fast enough in order to enter the water cleanly, they tuck, using their knowledge of physics, into a tight ball and use that technique to increase their rate of rotation. And so the question is, just how fast are they rotating tucked into the tight ball compared to when they are just straight out like a cylinder? Now I'm going to give you the inertia of a cylinder and the inertia of a ball to help you solve this problem. Right, here we go. A cylinder rotating about an axis that goes through the round part of the cylinder, right through the center there, is 1/4 mr squared plus 1/12 ml squared. I'll leave you to think about which one of those two components is more significant. The inertia of the tight ball is 2/5 mr squared. So, calculate the initial inertia, then the angular momentum, conserve the angular momentum to work out what that final velocity is. Pause the video and do it now. I don't want you cheating. It's interesting to see that the part of the inertia that's due to the radius of the cylinder is almost negligible compared to the part of the inertia due to its length. So we could almost have modelled this as a thin rod with negligible radius and got almost the same answer. Interesting, isn't it? So hopefully you got 26.8 kilogram meters squared per second for your angular momentum. Conserve it and work out the final velocity. And so hopefully you got an inertia for that solid ball of 3.84 kilogram meters squared, and then rearranged to get omega equals L upon I, and got 6.98 per second as your angular velocity. Trying to make some meaning out of that. Remember that 2 pi is 1 revolution, so 2 pi per second is 1 revolution per second, and 2 pi 6.3-ish. And so angular velocity here, just a little bit higher than 6.3, a little bit faster than 1 revolution per second, whereas over here, 2 per second, the angular velocity was about 2, it's about a third of 6.3, so around about a third of a revolution per second. And so we've tripled the angular velocity. Interesting to question what might happen to the rotational kinetic energy. Next time.